religioso o l'esperienza religiosa è innanzitutto un fatto, un fenomeno obiettivo, un fatto reale, non è un'idea, innanzitutto non è un modo di sentire, non solo si tratta di un fatto, di un avvenimento, ma del fatto più imponente e più inestirpabile della storia dell'uomo. Più imponente, più vasto, che neanche il fenomeno dell'amore dell'uomo e della donna, che neanche il fenomeno del rapporto tra genitori e figli. Perché il senso religioso è un avvenimento che pone, che afferma o che ricerca l'orizzonte entro il quale acquisti senso anche il rapporto tra l'uomo e la donna, anche il rapporto tra genitori e figli. Perciò è più vasto, perfino di quelli.
Dieci racconti di solidarietà e aiuto concreto, storie ricche d'amore, riscatto, coraggio e cura, storie di persone che donano e che ispirano a costruire una società inclusiva. Una mano a chi sostiene. Storie.
Il senso religioso o l'esperienza religiosa è innanzitutto un fatto, un fenomeno obiettivo, un fatto reale, non è un'idea, innanzitutto non è un modo di sentire, non solo si tratta di un fatto, di un avvenimento, ma del fatto più imponente e più inestirpabile della storia dell'uomo. Più imponente, più vasto, che neanche il fenomeno dell'amore dell'uomo e della donna, che neanche il fenomeno del rapporto tra genitori e figli. Perché il senso religioso è un avvenimento che pone, che afferma o che ricerca l'orizzonte entro il quale acquisti senso anche il rapporto tra l'uomo e la donna, anche il rapporto tra genitori e figli. Perciò è più vasto, perfino di quelli.
Dieci racconti di solidarietà e aiuto concreto, storie ricche d'amore, riscatto, coraggio e cura, storie di persone che donano e che ispirano a costruire una società inclusiva. Una mano a chi sostiene. Storie.
civiltà dell'amore. Fratelli e sorelle, costruite senza stancarvi mai questa civiltà. Lavorate per questo, pregate per questo, soffrite per questo.
Good evening, everybody, and welcome to the meeting of this evening, which is called Nuclear Fusion Energy from the Stars for the Future of the Planet. This meeting is organized by the Euresis Association in Rimini. There is maybe no physical process more evident than nuclear fusion, which makes the sun shine by day during the day and the stars during the night. The scientific insight of this phenomenon is less than 100 years old, with the discovery from the British astrophysicist Arthur Eddington, who published an article in 1926, and he started this path. From that intuition came a path, arduous and fruitful, that involves two only apparently distant aspects of scientific research. On the one hand, the study of the evolution of stars, which allows us to understand how the stars that we see every day, every night, and they all look like the same, being the same, and they have their own life, which is full of changes. And on the other hand, the energy source of the stars is also the source of every form of energy that we have available on our planet. And there is maybe a possibility, a way to reproduce, or rather to reinvent star fusion on our planet, making it, maybe, if we are wise enough, an even more hospitable place. Our two guests this evening will take us along this essential journey, which is fusion in stars and fusion on Earth. We have here with us Marcella Marconi. Marcella Marconi graduated in physics at the University of Pisa, and later she achieved a PhD in astronomy at the University of Florence. After a short activity abroad, she joined as a researcher the Capodimonte Observatory, which is part of the INAF, where she has a brilliant scientific career with important collaborations in Italy by coordinating research projects and also collaborating with the European institutions such as the ESA and the GAIA. Marcella's scientific activity is mainly focused and mainly concerns the study of sun luminosity and brightness variability and its application to the measurement of cosmic distances. Since 2018, Marcella has been director of the Capodimonte Observatory, and she also works as a research and management in the activities by teaching at the University Federico II in Naples. So welcome, Marcella. And then our second guest for this evening, Ambrogio Fasoli. Ambrogio Fasoli graduated in physics at the University of Milan, and then he achieved his PhD at the Ecole Polytechnique Fédérale de Lausanne. Then he moved to the Joint European Torus, the JET, and last year we had a short description of the last results that they achieved, which is still the largest device in the world for the study of thermonuclear fusion. He took part in the first experimental campaign with the deuterium and tritium fuel that produced the record-breaking fusion power produced in the laboratory. After a period spent at the MIT in Boston, he went back to the EPFL in Lausanne for teaching and research Among his activities, there is the construction of the TORPEX device for studying turbulence in plasma and the coordination of the activities of the tokamak TCV for thermonuclear fusion research. Since 2013, he's been working as a director of the Swiss Plasma Center, which is one of the best international centers for fusion research. Since 2019, he's president of the European EUROfusion Consortium, coordinating fusion research activities in Europe, and recently he's been appointed as a program manager of the same consortium, so he will therefore head the activities of this consortium starting from next January. Ambrogio also relies on online tools involving thousands of publishers every year. So welcome, Ambrogio, here with us this evening. So as you can see, we have two very important guests here with us this evening. So I leave the floor now to Marcella, who will show us how the nuclear energy is the engine of stars. Thank you to the organizers for this invitation to the meeting in Rimini. It's a real pleasure for me to be here, and I will talk about nuclear energy from the astrophysics point of view, so talking about the stars. Stars are objects that are working, as we will see, thanks to nuclear energy. So our life depends on a star, which is our sun. Basically, our life depends on nuclear energy that is produced by the sun. Before actually focusing on this topic, I'd like to briefly introduce myself, as it's been said. So I'm the director of the Capodimonte Observatory, and the Observatory of Naples, Capodimonte, is part of the Astrophysics National Institute that, as you can see here from this slide, we have several different headquarters in different regions in Italy, and Naples is the only one based in the southern Italy, which is a point of reference for different regions. And the National Institute for Astrophysics is focusing on astrophysics in Italy. Capodimonte is a medium-sized observatory, and you can see all the other observatories in Italy. So our observatory started many years ago. I'm not saying this is a very old one like a museum, but actually what I want to say is that there is no place in Italy which can actually develop real observation. On the one hand, because of the light pollution, which is too often too strong in our cities, preventing us to actually observe news and observe what we would like to do, and also because there are other places in the world where we can rely on big telescopes and big devices in order to make these observations, which are better than Italy. So the observatory was started 200 years ago, and we can say that this scientific activity in Naples and in other Italian observatories, of course, evolved. Of course, we are no longer doing what we used to do in the 19th century. In the past, we used to rely on the so-called position astronomy, so basically the position of stars as a support for navigation or for to find out and define the coordinates. And then we had further developments in physics and chemistry, and now also in our field we are focusing and talking about physics of the stars. So we want to know now how the stars are working, and from this topic we focus on this meeting event here, so understanding how stars are made, how stars are working, because we apparently see the stars, but we cannot actually understand if a star is brighter than another or not, or if it's just closer to us. Because we may think that the sun is the brightest star of all, which is not the case. It's just the closest one. So in order to understand how actually bright the stars are, we need to know their distance, and we need to know how they're working. So the scientific activity today in Capodimonte, but in all the national Institute of Astrophysics is focusing on several different fields, so focusing on planets, observation of the solar system, but also the discovery of other planets which are present in other stars around the Sun, and the study of galaxies as well. And there are, of course, technicians, engineers, and many experts that are actively and proactively working to develop further research and to achieve further important results in our field. So we are involving many technicians like biologists and other experts. Let's talk about stars. Star evolution is one of our core activities. What can we observe when we observe a star? Mainly we focus on two different sizes, two different elements. So we can say how bright they are or how bright they look. So we can measure the brightness of the stars, basically the quantity of radiation that we can collect, we can see with our devices, or their magnitude. And the other element that we can observe is how the energy of stars is actually distributed. So what we define, what we call the color of stars. So the blue stars are the warmest one, and the red ones are the coldest ones. And this is linked to the energy of each star, basically how much radiation and how this is distributed. Now, how is this linked to the nuclear energy and what we can learn about stars? At the beginning of the 19th century, there was this attempt to describe stars with a scheme in order to understand what was the real brightness of the stars. So on the horizontal axis, these two men stated the temperature, and on the vertical axis, the brightness. And they understood that stars are not distributed by chance. What they observed, and what we can still observe from this scheme, this is a very recent scheme that has been achieved with the Gaia satellite, which measures the distance of stars in the Milky Way. So if we have the distance, the brightness that you see stated there is the actual brightness, not the apparent one. So we know how distant they are, and we know how actually bright they are. And you can see that the majority of stars are distributed in this so-called main sequence, principal sequence. And why is that the case? There are brighter stars, colder stars, warmer stars. So why is there this kind of relationship? Well, the evolution of a star and people working on the evolution of stars are mainly focusing to try to interpret this kind of sequences, trying to understand why stars are distributed along this line and what is the engine which actually rules, which governs their work. If you focus on the Pleiades, for example, which are the so-called seven sisters, the one that we can see during the night. And if you put these stars, which are all at the same distance, even though we don't know the actual brightness, but it is as if we knew that, we know the distance of these stars, you can see that the brightness and the colors, again, are distributed with this diagonal sequence. This is a young object, a young mass compared with our galaxy. And there are also older masses of stars which have an age closer to our galaxy, which are made by millions of stars, where they have a spherical symmetry, and we believe that they are close to the age of the universe. And in that case, again, with this globular cluster, we see that the majority of stars are distributed along this line. So again, we have this main sequence. So what do these stars in the main sequence have in particular? Why are they distributed in that way along that line. So before answering this question, we need to understand how a star is made and how a star works. So a star is, we can define a star as a sphere of gas, very hot gas. They are made by hydrogen and helium, which are elements of which is made the universe, basically, because the universe was created mainly by matter, in which we can find hydrogen and helium. So it's a huge sphere of gas, which is kept together by gravity. So this means that if there was nothing else, this gas, this mass of gas, would finally arrive into a specific point, and we won't see the star. So if we think if we think at the sun, for example, we see the sun always with the same size. We don't see it smaller or bigger. So there is a force which works in a compensation of with the gravity, and this is due to the actual engine of the star, which is nuclear energy. And stars are born in the huge galaxies. So, for example, our galaxy has a shape of spiral, the Milky Way, and there is a plan with these real spiral shapes where stars are created. The one that you can see in the picture is Andromeda, actually, because we are in the middle of the Milky Way, so we will never see it in that way, but we can see that way our close, let's say, closer galaxy, which is Andromeda. And our galaxy, as it is the case for Andromeda, has a huge amount of stars. So there are 100 billion stars like the sun. If you think that the sun is one of these 100 billion stars, and the sun has a system of planets, and there are many other stars that we are discovering, so you can imagine how huge is the quantity and the number of stars that we are talking about. And apart from galaxies that have hundreds of billions of stars, we have fields like this one, which has been observed by the James Webb Telescope, which was recently launched. And this device is providing us wonderful images. And you see each, let's call it, little stain in this image is a galaxy. So galaxies that contain hundreds of billions of stars are very numerous. And if we have a look at where we are in our planet, turning around the sun, and the sun is not even in the center of the galaxy. It's just, we can say it's on the suburbs of the galaxy, of the Milky Way. So we can say that within the galaxy, stars are created where there is the material to create a star. We said that stars are huge spheres of gas, and they require this gas. And the presence of gas and powders can be found on huge clouds, which have the mass, which have a mass which is much bigger than our sun, which have a very, very cold temperature, from minus 250 to minus 100 degrees, more or less. So you can see these huge clouds, these images that we had from the space. These are regions where stars are burning. And what happens then? Basically, at a certain point, these clouds of gas create the so-called protostars. So with the effect of the gravity, these protostars collapse on themselves. So there is a kind of clots that are created, and we call them protostars, and because of the gravity, they collapse on themselves. So this goes on until when the core, the center of the star, achieves a certain temperature, and this starts the first important fusion process in the life of the star, which is the hydrogen fusion. So the hydrogen fusion happens at around 10 million degrees. So when the star collapses, it becomes hotter and hotter at the core, and when the temperature reaches 10 million degrees at the core, the protostar becomes a star. And we can say that a star is actually a star only when the nuclear fusion happens. Before it's a protostar. So this ignites, and we have the fusion of 4 nuclei of hydrogen. And they create a heavier nucleus, which is a nucleus of helium. So at this temperature, because of the fusion, 4 nuclei of hydrogen create 1 nucleus of helium. And this is what is happening in our sun. If we have a look at the sun, at the surface, it has a temperature achieving approximately 6,000 degrees on the surface, but at the core, it reaches 10 million degrees. And that's where this fusion process is happening. So that's the way we see our sun. So there is a nuclear fusion in the core, then a radiation area where the energy is transported. Then we have the convection zone. And then we have the part with all the of the sun's atmosphere, which characterizes all the external part of the sun. So that's how the sun is made. So the main sequence is not a sequence which happens by chance or just because of a coincidence, but this is the actual place of stars in that phase, in that stage of their evolution. So all the stars that are transforming hydrogen into helium are placed along this line. Actually, not all protostars become stars. So what happens then? Well, it may happen that during this collapsing stage, the structure is not strong enough in order to achieve the temperature of 10 million degrees. There are the so-called mist stars. So they are too little in order to start the hydrogen fusion, and they will never become a star. They are the so-called brown dwarfs. So if you can see on this slide, we can see Jupiter here, which is a planet, it's not a star. Then we have the so-called mist star, which is the brown dwarf, which is not much bigger than Jupiter. And then the smallest star which may be created, which is 1/10 of the mass of the sun, and then the sun, which is huge. So it's very important to understand which stars will become a star and which ones won't. So what are the smallest stars in the universe? And we believe that the smallest stars in the universe have approximately 1/10 of the mass of the sun, depending on their chemical formula. But this is the limit. This is the minimum mass in order to have a star. Smaller masses than that will become protostars, but they will never become a star. They will just become the so-called mist stars.
So this is what marks the stars on the main sequence. It is also the longest stage of an evolution of a star. Stars remain in this evolution phase for 90% of their lives. So our sun, which is aged 4.65 billion years, is about halfway its hydrogen combustion phase. So for other 5 billion years, it will continue to burn hydrogen into helium, and then it will have a more rapid evolution afterwards. The reason why we see almost all the stars on the main sequence is because of statistic reasons. Statistically, when we observe the stars, we observe more stars on that segment because that's the longest part of their evolution, whereas the other parts of the evolution are much more rapid. So the fusion of hydrogen is a nuclear reaction marking the lives of stars almost in their entirety, 90%. So you have 5 minutes left. So what happens when hydrogen runs out? When hydrogen is no longer there, the nucleus becomes an inert nucleus of helium, and there's a shift towards the yellow nut, transforming hydrogen into helium around the helium nucleus. In this stage, the stars become red giants. What will happen to our stars in 5 billion years? A much brighter object of the current sun. This is the branch of the red giants. You see it better here. On the left-hand side, the sun as it is today, and on the right, the red ball, the red balloon, the sun in 5 billion years time. It will go far beyond the orbit of the Earth. That is going to be the evolution of a star exhausting hydrogen at its core and having hydrogen combustion all around it. Then what happens? At a certain point, the star, as you saw, there's a helium nucleus at the center. Helium also starts to melt. 100 million degrees are reached as a temperature, and another nuclear fusion is carried out, helium producing carbon. As is the case of hydrogen, the protostars having more than 1/10 of solar mass were able to activate hydrogen fusion. Only those having half of the mass of the sun also managed to burn helium. The other ones stopped before that phase. This is the phase of the helium at the center. I will go more rapidly, and then at a certain point, the star having a smaller mass will lose their external layers due to the star wind, and they will become white dwarfs. Before becoming white dwarfs, they give rise to very beautiful objects. The planet nebulae are very, very beautiful, and the external layers are present. This is a material which is mist, and it shapes very, very good pictures. This reminds you of an eye, or this one which resembles a cabbage or a flower. And this seems a seashell. If you have a look at the internet, you will come across very beautiful pictures. That's the preamble, the prequel of the more inert phase, that of the white dwarf, which is the destiny of our sun, as well as of the all the less massive stars. Only the biggest, the more massive stars will manage to produce, in addition to helium, carbon, oxygen, all the heavy elements until up to iron. They become objects having an onion kind of shape. You have an iron nucleus and then other elements, lighter elements towards the outer part. Why do we stop when it comes to iron? Because, as we will see, the reaction of nuclear fusion is favored from an energetic point of view only up to iron. From iron onwards, fission is more favored. So that gives rise to an instability phase. This is why the more massive stars, instead of evolving towards an inert phase, such as that of white dwarf, explode as supernovas. When they explode, release all the elements that they have synthesized in their core. If Big Bang gave rise to hydrogen and helium, after the first stars exploded, the universe material will not be the same as it was before. It will be a contaminated material from all the products of the nuclear fusion events occurring in all the stars. So the more stars explode, and the more the material will be contaminated. Our sun has a much higher amount of heavier elements. vis-a-vis the older stars, because they were formed out of less contaminated material in comparison to the sun. And the stars that are forming now are even more richer in metals. So all the elements up to the iron are synthesized within the stars through nuclear reactions. What happens to heavier elements than iron? These elements are also synthesized by the stars with a different mechanism, by capture of neutrons or protons on pre-existing nuclei, either during the normal star evolution or, even more importantly, during the explosion of supernovas. So we'll now draw to a close, because I think now it is the moment to leave the floor to my companion. So we are really sons of the stars, sons and daughters of the stars, because all the chemical elements that also form us are formed in the stars, and we are all dependent on the stars, because our sun, which is a star, gives us life, but also functions through the nuclear fusion. We will listen more about in the contribution of the next speaker. Thank you very much. Thank you very much, Marcella. So we now leave the floor to Ambrogio. Ambrogio will explain to us how it is possible to try and reinvent this process on the Earth. So the floor is yours. Thank you very much. I'm very honored to be here. I'm glad to be here. Pleased to talk a little bit about fusion from the point of view of the Earth. After this wonderful presentation on the space, I will bring you back to the Earth, because what we want to do is solve a practical problem. We should build a star on the Earth. I do not have to remind you of all the energy-related problems that we have in our world, but I want to motivate this kind of activity with a picture I like very much. This is the picture of the world. It's a world map. Showing you the surfaces of the countries as corrected vis-a-vis the consumption of energy per capita. So the energy consumed by all the people living in the countries. This gives you a visual depiction of the north and south parts of the world. It's a very, very precise image. There's a whole part of the world which is almost totally deprived of energy, in which millions or billions of people have no access to electricity. And this part of the world is also the part of the world which is developing more than all the other areas of the world from a demographical point of view. So who are we to say that we are entitled to put the health of the planet at risk? We should stop. We have reached our level of consumption, but we cannot prevent the other parts of the world from using energy and from having access to the energy. They should use energies in a sustainable way without going to the detriment of the planet. Clearly, we are not in competition with renewable energies. No one can deny that our future, when it comes to energy, will depend a lot on renewable energies. No one today, I think, can claim that we can only use renewable energies. We already saw in various countries, such as Germany, for example. Germany made lots of efforts to develop renewable energies, but in parallel, they realized that they also needed basic energies accessible where and when we need it. So they built dozens of coal plants, exactly what shouldn't be done in order to preserve the health of our planet. So we need basic energy, because renewable resources need to store energy. They are intermittent, so we need to have basic energy, but it too should respect our planet, so not basing itself on the combustion, which is at the basis of the greenhouse effect. And this basic energy should be found in nuclei. This is my opinion, and the previous speaker explained to us where we learned. We learned by observing the sun, by observing the stars. We understood that if we put together very small nuclei, very small particles, hydrogen, which is the simplest element, if we put them together, they form slightly heavier nuclei with no problems related to waste products, because they form helium, which is a resource we should have greater access to. When we put together this nuclei, the overall mass is smaller than the mass that we had at the beginning. What happened? That the mass that is equivalent to the energy, thanks to what Einstein discovered, transformed into energy, and this energy is available to create electricity, for instance. The process of fusion we just carried out in the stars, with involving all the elements up to the iron, is exactly the opposite process of nuclear fission, feeding the plants that we have today. Fission breaks the radioactive heavy nuclei, creating relatively heavy and radioactive nuclei and other elements such as neutrons, which create chain reactions. In doing so, this process releases a big amount of energy. So fusion means putting together the light nuclei. Fission means breaking them, creating energy, but also creating radioactive waste products. So we understood how stars work. About 100 years ago, we understood that all the energy comes from the stars. We accumulated in hundreds of millions of years fossil energy coming from hydrocarbons that we burn every day. 80% of our energy, unfortunately, comes from hydrocarbon burning, and we will have several hundreds of years left. So why shouldn't we take a star and build a star, a copy of the star on the Earth? That was the dream of Prometheus, the Titan, the friend of mankind. Prometheus wanted to bring the sun to the humankind. We are at the point in which we cannot postpone this transition more than we already have, because it would be too detrimental for the planet. So we understood how fusion occurs, how it functions. Marcella explained it very clearly. Why don't we have fusion yet? Because it's not easy. It is very difficult to put these nuclei together, because nuclei, as you know, and you can see this in this short movie, have a positive charge. They do not like one another. They need to be they need to clash the ones with the others, so that they come as close as possible to create a fusion reaction. And this means that they need to have a very big, disorganized energy, high temperature. High temperature means, as Marcella said, it doesn't mean 1,000 degrees, not 40 degrees as we have today. It means dozens of millions of degrees. So processes taking place in dozens of millions of degrees. What is there? Well, nothing we are accustomed to using on the Earth. If we take ice, the solid ice, heat it becomes water. Then, if water is heated, it becomes vapor or steam or gas. What happens afterwards? A nuclei will go on one way. Electrons will be free to move in all the space. There's a sort of a soup made up of negative and positive charges, which we call plasma. The astrophysicists call very hot gas. It is a fourth state of the matter. It seems very exotic, and it is indeed, because on the Earth it is what makes up the majority of the universe as we know it. So this plasma should be created on the Earth, because we can have nuclear fusion only provided we have dozens of millions of degrees. So the life for a star is very easy because a star is big. Being big, it has an enormous force of gravity, and it can it is allowed to keep all these systems together, and it can also afford to take dozens of thousands of years. What reaches us was produced lots of years ago. We must be smarter and more rapid than the stars. It is not so easy. Once again, we need to take a reaction, and I will not enter into details. However, it is a rapid and effective version of what happens in the sun between two isotopes of hydrogen, two different versions of hydrogen. It is a reaction producing helium for a nuclei of hydrogen. And we also have a neutron bringing energy, a small particle with no charge, heating the water so that turbines can work, and it enables us to regenerate our own fuel. So we've been battling for dozens of years because the potential advantages are clear to all. So we have an enormous density of energy. So this is the stadium, San Siro Stadium. Because I come from Milan, this is why I decided to give you this example. The San Siro Stadium has about 80,000 seats in order to give energy to the city of Milan with fossil fuels. We need to fill in the San Siro Stadium completely until the third ring with carbon. Imagine how many thousands of trains should reach Milan every year. I should not say if, but when nuclear fusion will be available on the Earth. So I could bring the necessary fuel with only a bicycle. The consequences that the fuel that we have is inexhaustible. So some colleagues calculate that we have a possible nuclear fusion for 2.6 million years. So the impact on the environment will be reduced because there will be no greenhouse effect. And so there are no radioactive debris. And then another important thing for me, and what we do in the approach that we will dwell with later on, is that it has no major interests. No one can come to us and take and steal secrets. And this is important. It is a concentrated energy. It is not intermittent. So it is always available. We do not have to wait for wind to be there or for some rays to be there. It is not based on the concept of chain reaction unless we make mistakes in controlling this star. So as I said, the sun, the stars work by gravitational confinement. What I mean with this is that they keep together this soup of particles that would like to go everywhere only thanks to their gravitational force. We cannot have an energy plant that is bigger than the Earth, of course. We have two more options available. The possibility to use magnetic fields, and I will talk about this because it is the more credible and affordable possibility. And then another possibility, that of having inertial fusion by way of small explosions. You manage to keep this very small star in the place only because it has inertia. So it needs a finite time to escape. And I will give you an example of what's what was done recently. Recently, you read on the papers that twice, the second time was some weeks ago, more energy than was injected in this peel, the pellet in English, which is as big as a pupil of a human eye. This is the National Ignition Facility in California. This experiment was carried out here. 192 laser rays are injected. They are controlled by a control room. They are generated, then they are amplified. They are conveyed, transmitted in a plant which is very big, 4 times a soccer field. In the end, these laser rays are injected on a human pupil, a very small pellet, which is suspended. They need to reach this pellet exactly at the same time, in the same place, exactly at the same point. Otherwise, a mini star that is formed would escape everywhere. They managed to obtain more energy than the energy that was injected and reached the pellet. It is an enormous progress from a scientific point of view, but not in this way, because the laser rays, in order to bring this energy, need a lot more energy themselves to be produced, 300 times more energy. So we should improve this efficiency even more. This pellet is made of diamonds, gold, and even more complicated elements. As you can see, this is a billionth of a second, and each time it is subject to a small explosion, so you need to collect the remains of the explosion, and this is done once every 3 months. You should do it 10 times a second for this to function as a source of energy. They continue to carry out these experiments because they need to understand how it works properly. But I'm interested in carrying out a nuclear reactor on the Earth functioning 365 days a year for dozens of years, because the investor needs a return on the investment. And so I go on to the magnetic confinement, and I will show you another small movie. And we get inspiration from the nature. Once again, this is 100 million degrees. It is very unstable. But we saw that this hot gas, as my colleague called it, we call it plasma, is everywhere in the universe. So we believe, how should we not exist? We don't want to be ionized, of course, because we are protected by an extraordinary thing, by the magnetic field that the Earth has around itself. You know that we have 2 poles. We have a magnetic field around the Earth, which is a cage protecting us from the plasma coming from the sun, for instance. So we may have a reverse kind of cage. So we could confine the plasma so that the plasma cannot escape. This is why we thought about how to make a cage, keeping this star together, because we want to heat the star and take in energy out of it so that it does not escape. You may say that it is not so easy to heat it. It is one of the easiest things. We carry out a vacuum, so we take everything away from the machine. So we instill just a drop of gas. We heat it with microwave strands. We collaborate with several Italian laboratories, and we have millions of watts, like 10,000 microwave ovens. What happens if 10,000 microwave ovens heat up a tiny bit of a steak? We do it 20, 30 times a day, 4 days a week. So it's not such a big problem. The problem is to keep them together with magnetic confinement. We do it several times a day as well. So the idea of a very efficient cage came in Russia in the 50s. This is the tokamak, which is a Russian acronym. It is made up by various types of magnetic fields preventing the small star that we have created from escaping everywhere. It is quite a complicated object, as you can easily imagine, which made progress in the ability to control and to confine this very big and hot plasma. We've made some progress, some enormous progress. So you should come up with a fusion. The progress we've made in terms of parameters determining the distance from the final reactor were more rapid than the progress made for microchips when it comes to computers. So we cannot complain, but we are still not there because we are actually placing more power, more strength to the plasma than the energy that the plasma gives us back. So we need to take this step forward, and this step forward will be taken by all the researchers together. So with no fierce competition, we need to be totally open when it comes to information. We do it at the European level, at the world level. At European level, with no false modesty, we are the pioneers of this kind of community approach. Fusion was one of the key elements at the beginning of the European Union, and then it was an important part of common joint scientific projects. We have a EUROfusion. We have a consortium now made up of 29 countries, not only those of the European Union. We have Switzerland, we have Norway, and we have the United Kingdom and Ukraine, which is our partner. We have over 30 research institutions, 150 universities, 4,000 fusion researchers and support staff. We do everything together. There are several experiments which are being carried out. One is very, very important in Frascati, close to Rome, and each experiment does whatever it can do to provide crucial information to reach the final target, that of having a nuclear fusion reactor. Last year, we had a nuclear fusion reactor smashed energy record, the Joint European Torus, and I had a privilege of working there for several years. We still work all together. We obtained a record of energy fusion. We doubled the fusion energy. When you smash a record, it is very difficult to halve a record. You can increase a record by just a bit. We managed to double the fusion energy produced during an experiment. It was a very important thing because we did it in conditions that are the same that will be used for reactors. So we raised a lot of interest from the newspapers and the media.
Sure.
Let me also add a further remark, because I'm also working as a teacher and training engineers as well. And you can imagine how challenging it is every day to work on a project that will actually achieve a final result in tens of years. We have been working on that for 40, 50 years. People before me used to work on that. So with our young students, we don't only have to tell them, to teach them, well, you have to do that and then you'll get a result in a few months. It's impossible. We need to inspire them, and we need to look forward to the future. And I'd like to quote Antoine de Saint-Exupéry when he says that if you want to build a ship, don't drum up the men to gather wood, divide the work, and give orders. Instead, teach them to yearn for the vast and endless sea. That's what we need to do. When I ran a course online with my colleagues, I said this is on plasma. Of course, I said this is very challenging. There are thousands of students trying to learn these things. Scientific and technological demonstration of fusion will be done by the ITER project, which is an international treaty with 7 partners: US, Russia, South Korea, Japan, China, and India, and the EU, of course. Well, I say of course because the EU is the main partner and ITER is on the European territory in the south of France. That's an international collaboration, and all these countries are building components which are put together in order to make sure that at the end of this project, everybody has the responsibility to make this device working. Nobody can go into another country and impose themselves because they don't have the power, they don't have the ability to develop the power flow of energy. This is the most ambitious project ever done by the human being for peaceful goal. I took this picture a few weeks ago. That's the assembly stage. There are 10 million components coming from all over the world. You can imagine how challenging this puzzle is. And we are almost there in terms of assembly, as for the assembly. But this is not the very last step, because once we'll be able to show the technological and scientific possibility to do that, we need to demonstrate that we can sell the electricity. We need to be able to develop a power plant feeding hospitals and cities for years and years. And that's what the demo project will show, with an entire cycle of production of the fuel. And this will show the commercial aspect of the fusion. So showing how to reduce the costs and exploiting the safer aspect of this project. I don't want to go deep into details, but there are still some research and development elements which have to be achieved and completed before we can actually launch this project. We need to understand how to control the stars, which tries to escape everywhere. We need to understand how to manage safety in an active and proactive way, and how to optimize everything as if we were robots. And we need to be able to keep the plasma within this kind of bottle, because it's easy for the sun, which doesn't have any kind of container. We don't need to find an alternative, and we need to find a way to overcome this obstacle. We have a megawatt capacity per square meter, which is huge, 10 million watt per square meter. And it's very, very difficult because there is no material that can resist to this power. So let's imagine, for example, when there are the highest levels of power in the world that we know so far, we still have no possibility to have and rely on a material that can capture this power. We need to, for example, think to a satellite when it comes back to the Earth. It's 10 times less what we need here. What we're doing here all together in Europe, we are discussing, we are trying to find a solution how to achieve in a faster way these reactors. Of course, the geopolitical field always confirms us that we do not have to depend on a character or another, a country or another. We need to do that together, all together in terms of research, of course, running risks together, increasing investments together, involving industry and the private sector as well. And this is the new approach that we have in order to achieve this reactor, which will guarantee fusion energy and which will contribute in a very significant way to the problem of energy on our planet. And I'd like to finally show you a final video. We understood how sun is working. We understood how star is working. They need to be very hot. They need to stay together, the ones with the others. And in order to do that, we need to be able on the Earth to create a cage which should be efficient enough to keep this plasma. We know how to heat up the plasma, and we need now to be able to keep it together. And this will be the solution for a better future for our planet. Thank you. Thank you. Thank you for this very interesting speech. Both your speeches are very, very interesting. And of course, we have several questions that we would like to ask you. Marcella, the study of the variability of star brightness that you mentioned earlier, not only it allows us to understand the evolution of the life of the star, so in which stage the star is, but it also provides a kind of a tool to allow us to measure somehow the distances within our universe. This kind of understanding opens several different options. So what can we learn from this approach? Well, as we said, when we observe a star, we cannot understand what is the real brightness of the star if we don't know the distance of the stars. On the other hand, if we know the distance, we can understand how bright they actually are, and we can understand how they are actually placed and distributed in the galaxy and in the universe. In order to know this brightness, we need to have some objects that work as a kind of a sample in order to classify, to list the objects and to say that they are all bright at the same way. So if we see them brighter or less bright, they are more or less distant. Of course, there are also geometrical ways, to measure these distances, but this won't actually be the solution. You can go that far away, you can just reach the distance of the sun, but not far, not beyond the sun. So in order to measure distances more far away than the sun, we need to rely on the so-called variable stars. Variable stars means that the brightness and the dimension of the star is not constant over the time, but it will change. And it changes, in some cases, periodically, meaning that periodically the star will grow or will reduce its size, and the brightness will increase or decrease, again. If we were able to measure the time framework, so the distance between the two maximum of the brightness and of this object, we would be able to actually measure the actual brightness of the star. And this discovery was made at the beginning of the 20th century by a woman that has been able to discover the relationship between the measure of time, so the period between the two maximum levels of brightness of the star, and she found out the relationship between this time framework and the actual brightness of the star. This is a very powerful method that is still used nowadays, also on the very important and huge experiments that we run to measure huge distances, allowing us to understand how far away are the galaxies. So that's the kind of objects that we need to rely on. Or other very important and useful objects are the supernova. Supernova, as we said, are the results of the explosion of stars, and they are very bright objects, and they allow us to reach very huge distances. So if the supernova at the maximum of its explosions has a brightness which is related to a well-known distance, we can rely on this supernova as a sample, and we can measure very big distances. Thank you. Now, Ambrogio, a question for you. In your last slide, you mentioned a change of the pace, of the speed towards the achievement of fusion, and you mentioned some issues and some problems that still have to be solved. But actually, what is the real limit that we have to deal with today? What is the next obstacle that we shall overcome? Well, I think that the limit we have is the integration of all the aspects, because we need to be able to meet several different needs and conditions in order to have this star working as we want. So it should ignite and then stay in that status, so certain temperature, certain pressure, several technical parameters that should be met. And we can achieve these aspects individually, but we are not able to put them together. So it is as if we had 10 sports and we consider the average of the 10 best times that and records that can be achieved are different than those that we can achieve if we take the results individually. So we need to make sure that all the best results can be integrated and put together. That's the first thing. And the second thing, which is a kind of a consequence, is that, well, we are not aiming at being awarded a Nobel Prize. Our goal is that this thing shall work. It shall work not just once, but it shall have the potential to always work and keep on working. So these performances achieved individually are already a problem because they shall be achieved together, integrated. But the next step is to repeat them, and they shall work continuously every week, every year. So I think this is the crucial aspect of the research and the development at this stage. And when I talk about integration, I mean also integration of different cultures and different kind of approaches. So an academic and scientific approach with researchers, including and involving also the industrial approach, because there should be someone building these power plants, and they shall rely on simple, reliable results and approaches. And that's where we should focus, that's where we should speed up in a parallel way, and that's where we are focusing right now. Thank you very much. We are almost running out of time, even though I really would like to talk more in details about this topic. Let me stress once again the importance of the topics we mentioned. And first of all, I'd like to focus on the extraordinary unity of the universe in which we are living. The mechanism that ignites the stars, so distant and perhaps unreachable, are also at the basis of the matter which composes our bodies, each one with its own originality, coming from a chain of events that, taken individually, are simple and impossible to distinguish. And then a second aspect, which is, of course, the one of the huge, enormous scope of the change that the success of the technological and scientific approach into our society, providing to our humanity a technology that offers the possibility to significantly reduce the environmental impact of the energy production, but also the possibility to reduce inequalities thanks to the abundance of material and the fuel that we can produce. Of course, this should be a new resource and not a reason for new conflicts, which requires the consideration of the human experience as a friendship, on which the meeting this year focuses. And I think this is a fundamental aspect that Ambrogio also mentioned during the last part of his speech. Our guests will be available again to discuss with us and to go further into details about these topics, because of course I'm sure there are further questions. So tomorrow at 12:30 in the Piazza, the Hall 1, with the exhibition Gift and Resource, the Challenges of Energy, that I invite all of you to visit this exhibition, and you will have the possibility to ask further questions to our guests. Finally, I'd like to remind another thing, which is stated on all these panels. Civilization cannot grow without a culture, and the human existence is an inexhaustible friendship, and we need to have also an inexhaustible source. So each one of us, by taking part in the meeting, can contribute in a very important way in order to make sure this opportunity will become bigger and bigger as a representation of friendship, which aims at growing more and more between people and different cultures. So I kindly invite you to support the meeting with all the indications that you can find in the meeting, or simply clicking to sostienici.meetingrimini.org. So once again, thank you very much to our guests, and I wish you a very good evening.
Civiltà dell'amore, fratelli e sorelle, costruite senza stancarvi mai questa civiltà. Lavorate per questo, pregate per questo, soffrite per questo.
Il senso religioso o l'esperienza religiosa è innanzitutto un fatto, un fenomeno obiettivo, un fatto reale, non è un'idea, innanzitutto non è un modo di sentire. Non solo si tratta di un fatto, di un avvenimento, ma del fatto più imponente e più inestirpabile della storia dell'uomo. Più imponente, più vasto, che neanche il fenomeno dell'amore dell'uomo e della donna, che neanche il fenomeno del rapporto tra genitori e figli. Perché il senso religioso è un avvenimento che pone, che afferma o che ricerca l'orizzonte entro il quale acquisti senso anche il rapporto tra l'uomo e la donna, anche il rapporto tra genitori e figli. Perciò è più vasto, perfino di quelli.
Dieci racconti di solidarietà e aiuto concreto. Storie ricche d'amore, riscatto, coraggio e cura. Storie di persone che donano e che ispirano a costruire una società inclusiva. Una mano a chi sostiene. Storie.
Il senso religioso o l'esperienza religiosa è innanzitutto un fatto, un fenomeno obiettivo, un fatto reale, non è un'idea, innanzitutto non è un modo di sentire, non solo si tratta di un fatto, di un avvenimento, ma del fatto più imponente e più inestirpabile della storia dell'uomo. Più imponente, più vasto, che neanche il fenomeno dell'amore dell'uomo e della donna, che neanche il fenomeno del rapporto tra genitori e figli. Perché il senso religioso è un avvenimento che pone, che afferma o che ricerca l'orizzonte entro il quale acquisti senso anche il rapporto tra l'uomo e la donna, anche il rapporto tra genitori e figli. Perciò è più vasto, perfino di quelli.
Dieci racconti di solidarietà e aiuto concreto. Storie ricche d'amore, riscatto, coraggio e cura. Storie di persone che donano e che ispirano a costruire una società inclusiva. Una mano a chi sostiene. Storie.